1 drop of sodium hydroxide to 1 milliliter of water. Similarly, add 1 drop of HCl to another 1 liter of water. Does the pH change? Well, the answer is yes. The addition of 1 drop of acid or base to 1 liter of water changes the pH and makes it acidic or basic respectively. Now, you may add a drop of acid or base to 1 liter of a mixture of CH3COOH and CH3COONA. In this case, you may realize that pH of the solution is not appreciably changed with the addition of acid or base. Such solutions are called buffers. In this video, we will learn about buffers. Buffer solutions are solutions that resist the change in pH on dilution or with the addition of small amount of acid or alkali. The buffer can be acidic or basic in nature. How will you design a buffer solution? The knowledge of pKa, pKb and equilibrium constant help us to prepare the buffer solution of known pH. Buffers can be acidic or basic in nature. Let us start by discussing the preparation of an acidic buffer. For this, you have to use a weak acid and its salt formed with a strong base. Consider the generic equation for the ionization of weak acid in an aqueous medium and its respective dissociation constant. You may rearrange the equation as H3O plus is equal to Kaa minus by Ha. Upon taking log to the base 10 on both sides of this equation, you will get pH is equal to pKa plus log A minus divided by Ha. This may be generalized in the form pH is equal to pKa plus log conjugate base A minus divided by acid Ha. The expression is known as Henderson-Hasselbalch equation. Here, acid is weak, hence it ionizes only to a very little extent. Therefore, the Ha is almost the same as the concentration of acid taken to form a buffer. Also, most of the conjugate base A minus comes from the ionization of the salt of the acid. In such case, the concentration of conjugate base A minus will be negligibly different from the concentration of salt. Now, you may rewrite the equation as pH is equal to pKa plus log of salt divided by acid. Realize in the equation pH is equal to pKa plus log A minus divided by Ha. If A minus is equal to Ha, then pH is equal to pKa. Thus, we may conclude that at equal molar concentrations of acid and salt or conjugate base, then the pH of the buffer solution will be equal to the pKa of the acid. Hence, for the preparation of the buffer solution of the required pH, an acid whose pKa is close to the required pH is selected. For example, as the pKa value of acetic acid is 4.76, the pH of the buffer solution formed by acetic acid and sodium acetate taken in equal molar concentration will be around 4.76. Similarly, you may write Henderson-Hasselbalch equation for a buffer made with a weak base and its conjugate acid as POH is equal to pKb plus log conjugate acid divided by base. For basic buffer obtained by taking ammonia solution and ammonium chloride solution of the same molar concentration, the pH is close to 9.25 because the pKa value for ammonia is 9.25. How will you justify this? Well, let us relate the Henderson-Hasselbalch equation for basic buffer with Kw, the ionic product of water. You may recall the equations pH plus POH is equal to 14, which is pKw, and pKa plus pKb is equal to pKw. On putting these values in Henderson-Hasselbalch equation, you may get pKw minus pH is equal to pKw plus log of conjugate acid divided by base, or pH is equal to pKa plus log of conjugate acid divided by base. This means if molar concentration of the base and its conjugate acid is the same, then the pH of the buffer solution will be the same as the pKa of the base. Now let us discuss the importance of buffers. In fact, buffers play a vital role in many chemical and biological systems. Body fluids such as blood or urine have definite pH. Any deviation in their pH indicates malfunctioning of the body. Besides, medical and cosmetic formulations require that these be kept and administered at a particular pH. Now, before winding up the session, I would like to bring your notice to an important observation. Have you seen calcium chloride, which is hygroscopic? At the same time, there are compounds such as lithium fluoride. Did you notice both are ionic solids, but their solubilities differ? How will you account for the difference in the solubilities of ionic compounds? Think about it. Now, let us summarize what we have learnt.
Manorama Horizon. Learning made simple.